Hi, I'm Jasminder Sidhu, and in this talk, I will highlight how you can use linear optics and photodetection for near-optimal unambiguous coherent state discrimination. I'll start first with an introduction and overview before going into a summary of our results in designing receivers and their applications to different codes. This work can be seen in greater detail on our archive paper, which is shown at the bottom of the slide, and it was done in collaboration with colleagues from the University of Arizona that include Michael Bullock, Saikat, Guha, and also Cosmo Lupo from the University of Bari. So why do we want to discriminate quantum states? The question that we often address is how to identify an unknown quantum state ρx that is drawn randomly from a known finite set. Now, quantum mechanics places fundamental limits to distinguishing non-orthogonal quantum states, but fortunately also provides us with tools to approach these limits. And this is important to improve the performance in a range of applications, including cryptography and computing. So we often want to design quantum receivers that combine both practicality and high performance. Now, high performance depends on your figure of merit, which depends on the framework that you use. The first framework is unambiguous state discrimination, where the receivers always provide an output, and the goal is then to minimize the average error probability, which is ultimately governed by the Hallstrom limit. Now, the optimal receiver for more than two quantum states is generally unknown. The second framework is unambiguous state discrimination, where receivers are designed to identify the state without error, the trade-off being that sometimes you will get an inconclusive event. So the goal then is to minimize the inconclusive event probability, which is given by the Perez-Turnow limit, which we'll summarize in the coming slides. Now, a lot of the work in the literature have focused on defining what these global bounds are, and often do not consider the explicit receiver constructions, which generally are difficult to attain beyond a few examples. So this is something that we'll look at and has been a theme of some of our previous work, which is practical receiver designs. And at least for the ambiguous state discrimination, this work can be seen published in PRX Quantum. And for the remainder of the talk, we'll be concerned with the second framework, unambiguous state discrimination, where we'll use a practical set of resources to minimize the inconclusive event probability. To first define what the global optimal bound is for unambiguous state discrimination, consider linearly independent vectors uj with some prior pj. We define the vectors v such that they satisfy the inner product, and from this we construct our PLVM measurements. We can use this to define what our inconclusive event PLVM is. It's just 1 minus that. And the inconclusive event probability then follows. Now, this is the quantity that we want to minimize. And so the global optimal bound is just an optimization problem, which corresponds to the minimization of P0. The constraint ensures that the inconclusive event PLVM is positive. Now, as I suggested earlier, a lot of work have addressed this optimization, and this can be efficiently evaluated using an STP approach, or also semi-analytical solutions can be attained using geometric insights of quantum states. Now, we'll be considering a limited set of resources, which are linear optics, to enhance the practicality of our receivers. So we'll be concerned with multimode code words, so that's coherent states distributed across multiple modes. And the scalar product between multimode code words often follows this standard definition in quantum optics. And this scalar product is invariant under unitary transformations and underlies the general analysis of determining the global bound. Now, because we're considering a limited pool of resources, we want to consider an alternative scalar product that is more suited. We call this updated scalar product the phase space scalar product. And this is invariant under LOP unitaries, or for linear optical passive unitaries. Now, it's known that linear optical passive unitaries can be efficiently decomposed into a network of beam splitters and phase shifters, and so the limited pool of resources that we will refer to include vacuum auxiliary modes, beam splitters, phase shifters, displacement, and on-off detection. Note that we won't be referring to or making use of feedback mechanisms. So these won't be adaptive receivers. Now, under this limited pool of resources, we'll construct multiple receivers. So our class 1 of receivers, which use single mode detection. So on the left-hand side, what we're doing is mixing our signal coherent state modes with vacuum at a LLP unitary, and we consider just a single mode detection. So you can see just one across all the modes. Now, the optimized performance of this receiver is given on the right side. We derive this archive paper, so I'll refer to details to the paper. But the key outcome is that this is a limited set of resources, so you can see it's very easy to implement. However, code words must be linearly independent for optimal unambiguous state discrimination. Now, we can improve the performance of this receiver by increasing the pool of resources that we use to include displacement operations. So still under class 1 because we're using single mode detection, but now with displacement. As you see on the top left, we are now displacing the input signal states and then mixing it with our vacuum auxiliary modes at our LLP, and the photo detection events then follow. Now, the optimized performance of this receiver is given on the right-hand side. And the key outcome of this is that displacement operations are still easy to implement. But importantly, this receiver improves the performance and enables unambiguous state discrimination of single degenerate codes. Okay, now, as you can imagine, there will be a range of constellations or codes that you can imagine that have greater degeneracy. And so that this brings us to a class 2 of receivers where we make use of multimode detection. So as you see on the top left, an example is where we have a signal state and we mix it with vacuum auxiliary modes at LLP, and then we displace each mode before detecting 2 modes, which is shown by 2 ones across the mode. This is just an example. Now, the optimized performance of this receiver is given on the right-hand side. And the key outcome of this is that it enables USD of linearly dependent vectors, which is useful for a variety of constellations, so extends its use applications to many other examples. Now, codes with higher degeneracy can similarly be handled by enabling multiple detection events that are greater than 2. So as some examples, just to conclude, for PPM codes, what we find is that our limited set of resources is optimal and sufficient to saturate the global optimal bound. We also consider random codes where we construct the amplitude of our code words over 3 modes randomly with some mean photon number n. So shown in this plot is n equals 0.6, and what we compare is the distribution of inconclusive event probabilities that are possible for 3 of our receivers. In red, we show for class 1 receiver without displacement. In blue, class 1 receiver with displacement, and shown in brown is the global bound. And what we see is that our class 1 receiver with displacement is near optimal, with only a small difference in small p0 values, as you would expect. Now, we extend this to consider some degeneracy. So shown here is a code word example, a 2-mode code word example with single degeneracy. And in this case, our class 1 receiver without displacement is not able to unambiguously discriminate these states. So we compare our class 1 receiver with displacement to the global bound, and we see that it's near optimal for a range of different symbol intensities. Now, we can actually close this gap if we were to consider alternative figure of merits. And so that's what we do here. We compare now the performance for the same 2 receivers, but now considering the communication capacity as a function of the symbol intensity. And what we see is that our linear receivers saturate the globally optimal capacity. Now, we now consider the double degenerate code. So this is a single mode code at the top with double degeneracy. And in this case, both of our class 1 receivers is not able to unambiguously discriminate this. And so we necessarily have to use our class 2 receiver, which makes use of 2 detection events. And this is shown in red, and you can see that it closely follows the global bound shown in brown. And moreover, what we have is an explicit receiver design shown also in the figure, where we mix the input signal state with vacuum and also an auxiliary mode with amplitude alpha over square root 2. So as you can see, this highlights the relative ease in which this can be implemented. Now, there are also other examples, such as your phase shift keying, that's important for communications, that we do consider, but I'll refer you to our archive paper for that. So as a quick summary, we have developed a new theory for an unambiguous state discrimination framework using just linear optics and photo detection. We've provided explicit receiver designs for a range of different code words, and we find that they are often near optimal, which shows the strength of this work. Thank you very much for your attention.